My name is Vikas. I'm a postdoctoral fellow at the Aerospace Engineering Department at Auburn University. And I'll be presenting on behalf of my colleagues here today. And the topic of the presentation here is about the ejecta dynamics due to Plume-Surface interactions and its relationship with crater topology. Next slide, please. Next one. Okay, so as you already noted, Plume-Surface interactions are important, specifically during the touchdown and liftoff of lunar landers on the surface, and they are known to be associated with formation of craters, and which can lead to landers becoming unstable upon touchdown, and the erosion of particles from the surface, which can lead to particles traveling at very high velocities, and can be a source of hazard to structures and valuable scientific equipment in the vicinity. Next slide, please. So the scope for this study is that there are major challenges in developing a comprehensive understanding of this 3D phenomenon, especially considering the fact that the existing laboratory scale measurements are intrusive in nature. And secondly, there is a need to characterize the ejecta and cratering dynamics simultaneously to facilitate the development of models and predictive tools. Next one, please. So the objectives of this study are to understand the influence of the operating conditions on the ejecta evolution, specifically the atmospheric pressure conditions, or the ambient pressure conditions, moving from continuum to rarefied environments, and secondly, to identify and quantify if there are any relationships existing between the ejecta and cratering dynamics. Next slide, please. So in terms of the experimental facility, all the measurements were performed at the vacuum chamber facility at Auburn University. The facility consists of a nozzle assembly consisting of a constant area tube attached to a stepper motor assembly. A granular bed is placed at the bottom of the chamber, and it is filled up with sand particles and basically leveled on the surface. In terms of measurements, stereophotogrammetry technique was employed to extract the geometric properties of the crater. For more details, I would suggest you to look up the latest recent journal article in the AWA journal. And the second aspect is the measurement of particle tracking velocimetry for the ejecta dynamics. And this was basically performed by illuminating a laser sheet that passes through the axis of the nozzle. And the images are captured by a side view camera that is visible in this clip. Next slide, please. In terms of data extraction, so through stereophotogrammetry, we were able to extract the disparity map between the images acquired by the two stereo cameras, as you can see in this clip. And from these images, we were able to extract geometric features of the crater, such as depth, radius, and volume, and so forth. And in terms of the ejecta evolution, the particle tracking velocimetry yielded us metrics like particle velocities, ejection angles, and so forth. And using these metrics, we were able to model this and stitch a trajectory to these particles and extract features like the range and height traveled by these particles. Next slide, please. Now, going on to the results section, now let's start to look at some of the qualitative features that we observe in some of these interactions. So starting with the atmospheric conditions, the Earth atmospheric conditions that you see on the left-hand side clip, we realize that after the plume interacts with the surface, the particles are generally eroded at really steep angles. And ultimately, the crater that ends up forming is generally parabolic in nature or sometimes deeper. We'll go talk about it in the next few slides. And under subatmospheric conditions, or under rarefied conditions, we realize that particles are generally traveling shallower at an extremely shallow angle. And finally, the crater pattern that emerges out of this particular case appears to be lobed in nature. Next slide, please. So from these measurements, from the stereophotogrammetry and particle tracking measurements we have made, so we go on to make a comparison between the features that we observe across the subatmospheric and atmospheric cases. So under atmospheric conditions, we realize that the crater that you see in the first column is generally parabolic or deep in nature. It is generally deep when we are closer, when the nozzle height is generally shorter. But due to limitations in the reconstruction technique, we are not able to capture the depth of the crater under these conditions. On the other hand, the ejecta particles are generally traveling steep, as we observed in the previous clip. And under subatmospheric conditions, we realize that the crater pattern is lobed in nature, especially at larger nozzle heights, and they're parabolic at shorter nozzle heights. and the ejecta trajectories are generally extremely shallow compared to what we see under atmospheric conditions. Next slide, please. So from these measurements of the ejecta particles that we had obtained through particle tracking, we try to fit a ballistic model to the trajectories that we have ended up measuring. And the purpose for this is that we will be able to extrapolate the position, velocity, angles, and the range covered by these particles. And we realized that through the calculation of Stokes number of these particles, which are extremely high, we realized that the ballistic model would be fairly accurate to obtain the full trajectory of the individual particles that we obtain from the particle tracking velocimetry. So from this model, we go on to make a comparison between the trajectories of these particles under atmospheric and subatmospheric conditions, and represented by the red curve for the atmospheric and the black curve for the subatmospheric conditions. And if we go on to look at these features individually, we observe that under atmospheric conditions, the particles are generally having relatively lower velocities. They travel at steeper ejection angles. Their trajectories cover a larger height and a shorter range. On the other hand, under subatmospheric conditions, the particles have larger velocities, travel at shallower angles, and cover a smaller height and a larger range. Next slide, please. The next obvious step would be to identify what sort of relationship we observe between the particles' trajectories and the geometry of the crater that we have extracted and the measurements which were made simultaneously. So the first parameter we compare is the crater rim, which is characterized by the radius of the crater from the axis of the nozzle. And then we compare this with the particle ejection location, which is defined by the position of the particle closest to the surface of the undisturbed granular bed from where the particle is first getting ejected. This position was basically extracted by extrapolating the trajectory of these ejecta particles measured through PTV. And by making this comparison and their evolution over time, we realized that there is a significant correlation between the ejecta location and the crater rim, as you can see in the first plot on the left bottom side. And the next comparison was between the crater ramp angle and the particle ejection location. So the crater ramp angle is defined by the angle corresponding to the crater at the surface of the undisturbed granular bed. And then the ejection angle is represented by the angle of the particles, angle at which the particles are getting ejected closest to the surface of the undisturbed bed. So then make a comparison between these two particles, as you can see in the right-hand side plot at the bottom. You realize that there is a significant correlation between these two properties again, and suggests that the crater geometry and the ejecta properties are very well correlated. So go into the next slide, please. So this brings us to some of the conclusions from these measurements. So what we realize is the ejecta particles travel at very high velocities, relatively higher velocities compared to under Earth atmospheric conditions, at shallow rejection angles, and achieve a larger range and smaller heights in their trajectories under subatmospheric conditions. So the potential consequence of this is that there is a higher chance for damage and hazards to on-ground structures under subatmospheric conditions. And the second aspect is we identified that there's a strong correlation existing between the geometry of the crater and the ejecta trajectories, which can aid us and provide us a powerful tool to predict the ejecta behavior based on some of the in situ crater measurements that we can make on flight. So with this, we can go to the next slide. And with this, we would like to acknowledge the funding and support provided by the ESI NASA grant and our collaborators at NASA. And I would like to take up any questions if there is any. Thank you.